Okay, so today's lecture, now, given that we saw randomized quicksort and Kargar's mincut, we are going to dig deeper into sort of the bread and butter topic of randomized algorithms, and we're going to look into concentration bounds, and we're going to focus, significantly on things like, on the Chernoff bound. But let's begin. Just going back to our to what we did last time. We discussed two different algorithms. So we did randomized quicksort, and we did Kargar's mincut. Okay. So I'd like to what I'd like to do is sort of contrast these algorithms. So for randomized quicksort, we had an expected runtime bound. On the other hand, the error probability. Sorry.
Wait, I think Will says in the chat that he can't hear you. Sorry.
Can
you hear?
Can everyone else hear me?
It's kind of lag.
Yeah, but I think the audio is pretty good, right? Maybe just the video is slightly laggy, yes, last time, but that's still good, right? I think he might have a problem on his own end.
I see. Yeah, the video might be a little laggy. I think there's no fortunately that might be unavoidable. But certainly I can, I think most of you can hear me. So all right, so continuing, the error probability is 0. By the way, stop me at any point if something is unclear. Right? So randomized quicksort had an expected runtime bound. Right? The expected runtime bound was n log n, but there was no probability of error. The algorithm never failed. On the other hand, in Kargar's mincut, the runtime bound, the worst case runtime bound was just fixed. I mean, it was a running time bound with probability of 1. But there was a non-zero error probability. So there was a contrast between these algorithms, and this terminology, I guess, is not used so commonly anymore, although essentially these are referred to as Las Vegas algorithms and these are referred to as Monte Carlo. And what I'd like to discuss, and the discussion today, and which will extend into a few lectures, is really to understand what do you do with expected runtime bounds? Like, what can you infer from them, and do you get more information than just the expectation? So let's start with something simple. It's a simple exercise, but it's quite illuminating. You can convert an algorithm with an expected runtime bound but 0 error probability into one where the runtime bound is fixed, so it's a probability 1, but there's a non-zero error probability. So we can convert from here to here, but not necessarily the other way around. So let me show you how to do this conversion. So let's look at randomized quicksort. And we said that the expected running time was at most, and it was essentially at most c times n log n. C is some absolute constant. And just to be consistent, I will replace this with LG, which is basically log base 2, right? So C times n log n. So what we know is that randomized quicksort, so for all inputs of size n, the expected running time is at most Cn log n. But what does that tell you about can you get some kind of high probability statement? I mean, this just says that the average runtime is Cn log n, but maybe there are some situations or some choices of the randomness where it might be extremely poor. Can we get a better understanding of this? Sometimes what we want is to actually have a fixed runtime bound. Towards that, there's a nice trick to sort of convert a Las Vegas algorithm into a Monte Carlo algorithm, and that uses sort of our very first concentration type bound, a very simple bound known as the Markov inequality, also called the Markov bound. So the Markov bound says if x is a non-negative random variable, the probability that x, and let me say that k is going to be some parameter that is going to be greater than some positive parameter, the probability that x is greater than k times the expectation is at most 1 over k. Okay? I think it should probably be that. The probability that x is going to be k times the expected value is at most 1 over k, and this holds actually for all k. So essentially when k is less than 1, it doesn't tell you anything. But when k is large, it tells you that a non-negative random variable cannot be much larger than its expectation. And it's fairly easy to prove the Markov inequality. And you use the non-negativity here. So I'm not going to show you a proof of the Markov inequality. But I want you to look at the statement. And now let's go back and look at Quicksort. So Quicksort says the expected running time is less than Cn log n. So the probability that the running time is going to be, let's say, 10 times that is at most 1/10. So let me now give you, using this, let me give you a fixed version of randomized quicksort where the running time is going to be fixed. So I'll call this fixed randomized quicksort. I'm going to use a parameter here which I can then set later. I'll just say for d times. So d is going to be some constant. For d times, do the following. Run the vanilla version, the old version of randomized quicksort. So this is on some array. If the running time exceeds, and let's say that I can just put in some parameter here. If the running time exceeds, I'm just going to put some number over here so that we can quantify this. If the running time exceeds 2 Cn lgn, right? So I'm just saying that the expected running time is Cn log n. If your running time ever goes twice that, then just stop and run the next iteration. Right? So if it ever exceeds Cn log n, stop and then start afresh. Okay, so it's like an independent invocation. So you're running multiple independent invocations. And if it terminates, well, okay, then we're done anyway. So you're going to do this d times. Now the problem is it could be that every time you ran, the running time actually exceeded, so you went back and ran, and this kept failing. So if all of these fail, you'll just output failed. Okay? So this version of quicksort could potentially fail. But the running time, what is the running time of this algorithm? What is the running time of this algorithm?
N log n.
Sorry, repeat.
N log n.
It's basically n log n, or it's, technically we would say it's, it's basically it's c d n log n, and maybe there's some constant 2 or 3 or something over here, right? I'll just put 2, but it could be extra constant because of the extra operations. But you see, you just have essentially for cd constant, this is just O of n log n. So the running time bound is fixed. On the other hand, there is a failure probability. Okay? So now what is the probability of failure? This is, look at any individual iteration. In any individual iteration, if the running time exceeded 2cn log n, then it would fail. And this has to happen d times because there are d and there are d independent invocations. So because there are d independent invocations, this is essentially the probability that the running time of randomized quicksort exceeded twice cn log n, exceeded twice the expected running time. Right? So this is the probability to the power d. This makes sense? So the probability of failure is the probability that the running time of randomized quicksort exceeded twice its expectation d independent times. By the Markov bound, this is less than half, right? Because the probability that the running time exceeds twice its expectation is at most a half. And therefore, this probability is at most 1 divided by 2 to the d. So it's exponentially decreasing in d. So now we can essentially set d to be something like 10, and the probability of failure is going to be essentially 1 in 1,000. Okay? So this is a simple trick, but a very common one in randomized analysis, in the analysis of randomized algorithms, where you apply the Markov inequality. And the Markov inequality gives you a fairly weak bound. So you just do multiple independent invocations of those, and then you can get this sort of concentration. This idea, which we will be revisiting multiple times, is essentially some kind of boosting the success probability. Okay, so does this make sense? This is a very naive analysis, a very simple one that I wanted to show you just to introduce the Markov bound. Although what we're going to do will be much more sophisticated. So with the Markov inequality, what you can do is you can start essentially with a Las Vegas algorithm, which has an expected runtime bound but 0 error probability. And you can convert it into one whose runtime bound is fixed, but now it has a non-zero error probability, and there is a trade-off between these parameters. And the trade-off over here is essentially given by the d that is here. So as you increase d, you increase the runtime bound, but you exponentially decrease the failure probability. This is important. For a linear increase here, you get an exponential decrease here. So it's fairly cheap to to decrease the failure probability. And this feature, this fact that you do linear here and exponential over there, is going to become an important part of the analysis that we will revisit over and over again. So let me now begin. Let me now say, okay, this was a naive analysis. So any questions about that? Any questions? Okay, so let me continue. And
I actually had a question, if you don't mind.
Yes.
What does this tell us about RQ sort going over n log n time?
What does it tell you about RQ sort going n log n time? Maybe I don't understand your question.
Or like, because this says something about this new algorithm that we've created.
Oh, you're saying, yeah, so what can we say about the original randomized quicksort? That's your question.
Yeah.
Yeah, so that is exactly what I'm going to come to. And the answer to that will not be given in this lecture, but we will essentially build the tools to answer that question. And this is exactly the next point that I want to try. That was a naive analysis. Can we directly analyze randomized quicksort? For this, what we need is essentially we need concentration inequalities. We need concentration inequalities. We need to say, which essentially tell us under what circumstances does, so when I say RV, I mean random variable X behave like E of X with high probability. So what we would ideally like to say, we'd ideally like to say something like the probability that the running time of randomized quicksort is, at most, I don't know, I'm just going to put some numbers here, just is at most k times, n log n, with probability at least 1 minus some decreasing function of k. Some decreasing function of k. Right? This is what we'd like to say. Maybe this would, ideally you'd like to say, oh, maybe this is like 1 minus 2 to the minus k or something. I mean, this is not necessarily going to be true, but this is sort of the ideal bound. And actually, we can achieve something like this with some change in constants. And I will prove something like this eventually. This is what we would like to show. So this is your random variable x. And n log n is the expectation of x up to some constant. And you're trying to relate how often does x deviate from the expectation. Or instead of, behave like is a strange word, is how under what does random variable x, I'll say, be comparable to x. Or another way of saying this is, what is the probability that x deviates from the expectation? So let's start with the most common, it's a sort of simple concentration inequality, one that you've all seen, which is Chebyshev's inequality. And Chebyshev is going to be sort of weak over here, and then we'll discuss more inequalities. So what is the Chebyshev inequality? So I just want to go back to the Markov inequality. And just to answer the question of what can you say about randomized quicksort directly, well, you can always use the Markov inequality to get something. So the Markov inequality, if you apply it here, will say something like the probability is like 1 minus 1 over k. Again, up to constant. So I'm sort of, maybe let me put that constant c back in over there. So the probability that the running time is at most k times cn log n is at least 1 minus 1 over k. That's the Markov bound. And the question is it even better? Now the Chebyshev inequality might give you something better. So what does the Chebyshev inequality say? So the good thing about the Markov inequality is you don't need any assumptions about x other than non-negativity. So just by the fact that it's non-negative, you can say something. Chebyshev is going to say, well, if you give me more information about x, then Chebyshev will give you a better bound. So what do you need? You need to bound the variance of x. So what is the variance? The variance is the expectation of x squared minus the expectation of x whole square. And an application of Jensen's inequality will tell you that this is always positive. And so the standard deviation of x is the square root of the variance. What Chebyshev's inequality says is the probability, okay, so I'm going to write this down now, the probability, so this is your deviation. This is your deviation. The probability that the deviation is k times that, k times the variance, the standard deviation is at most 1 over k squared. This is the Chebyshev inequality. Now, we're actually not going to use the Chebyshev inequality today. But what I want to do is to demonstrate something about this bound, which is very important. You express your deviation in terms of multiples of the standard deviation. So you say the probability of having a deviation more than k times the standard deviation is at most something. And you see that you have a k over there, and you have a 1 over k squared over here. Again, to contrast with the Markov bound, I'll sort of put the Markov bound over here, try to put these together. The Markov bound says deviation in terms of just the expectation. And you have a k and a 1 over k. You'll see that there's a k and there's a 1 over k. The Chebyshev inequality says express the deviation in terms of the standard deviation, not just the expectation. So you need more information. You need to know what the variance is on the standard deviation, and you get a k and a 1 over k squared. Okay, so this is the Chebyshev inequality. But the point is actually not to use the Chebyshev inequality, but to understand a far stronger inequality. Often, x has structure and we can do better. So just to go back, so naively, I'm going to say naively, you could say that, I mean, this is not entirely true, although one could probably prove this, is that you could say the probability of the running time quicksort, this was x, is less than k times this. So if this was also comparable to the standard deviation, then maybe you could get 1 minus 1 over k squared instead. Right, if you were to apply something like Chebyshev. But often x has structure and one can do better. And so what is the structure? And this is going to lead us to the Chernoff bound. That if x is the sum of many independent random variables, I'm going to give you sort of an intuitive picture. Say if x is the sum of many independent random variables, then x concentrates much more sharply. Indeed, what I mean is if this tends to infinity, so is as the sum increases, x tends to a Gaussian. And this is really the central limit theorem. I mean, under certain conditions on these random variables, you know that if it's the sum of many independent random variables, then x is going to behave like a Gaussian. And one of the bread and butter techniques in randomized algorithms is when you analyze an algorithm, try to discover a random variable that is expressible as the sum of many independent random variables and essentially use what are called concentration inequalities to bound it. Okay, so let's just try to understand. You have Chebyshev here. Let me tell you approximately what does a Gaussian look like. So a Gaussian is going to say, what is the probability that x deviates from its expectation by k times the variance? So what does this look like in a Gaussian? So if you have a Gaussian, ignoring constants, can someone hazard the expression, hazard a guess as to what the expression is? What is the probability of deviating k times the standard deviation in a Gaussian?
E to the negative k.
E to the negative, almost, it's e to the negative k squared. So this is actually e to the minus k squared. So just to put some numbers, so you see, if k is equal to 10, so what is the probability of deviating by 10 standard deviations? Chebyshev says, well, the probability is about 1 in 100. And if it was a Gaussian, it's e to the minus 100. This is like astronomically small, right? This is like almost I guess what this would almost be like 10 to the minus 30 or something. So it's 10 to the minus 2 versus I guess 10 to the minus 30. Right? So the deviations are extremely small. Even when you put something like 2 or 3 standard deviations, this probability is extremely small. But here with 2 or 3 standard deviations, you barely get, you don't get much. The probability is still reasonably high. The probability here is extremely small. Now this is useful also as a rule of thumb. If you have a random variable that's not necessarily a Gaussian, but you're trying to understand how well it could concentrate, one rule of thumb is to simply assume it's a Gaussian and see what you get. This rule of thumb is usually there to understand sums typically independent, sums of random variables. So it's e to the minus k squared, which is astronomically small. So if one could argue this, so suppose we could bound the variance of quicksort, we could bound the standard deviation of quicksort. We said, well, suppose the standard deviation was also n log n. Then the probability of deviating from the expectation by some multiple of n log n is e to the minus k squared, astronomically small. And again, you have now this exponential dependence showing up. Okay? So so I'm going to sort of keep this visible. So I want you to sort of see that. When x has this property, and by this property I mean this property, then we say x has sub-Gaussian tails. And again, this is like bread and butter of analysis of randomized algorithms, is to discover random variables that are related to your algorithm that have sub-Gaussian tails. A significant part of the game is basically doing that. And so now I'm going to give you some theorems telling you under what circumstances, very special, simple circumstances where you have sub-Gaussian tails, but indeed these are mostly enough for analyzing a large majority of randomized algorithms. So before I give this, I had this thing called tails. So what do I mean by the tails? So let's just think of, I'm just going to draw a cartoon, and let's just say, roughly speaking, this is the probability, and I'm going to, let's say I draw like, the PDF, the probability density function of x. Okay, and let's say it looks something like this. Somewhere around here, this is going to be the expectation of x. These portions are called the tails. This is called the upper tail, and this is actually called the lower tail. And tail inequalities or concentration inequalities bound the probability mass in the tails. I mean, this is a cartoon, but typically this is really, really small. And this is usually what is like k times your standard deviation. So there's your random variable, sort of exists. Most of the probability mass exists within a few standard deviations. Then after that, it drops off very sharply. Now, the most basic concentration inequality, and this is called the Huffing Bound. Funnily enough, the Huffing inequality is actually a specific tool used in the Huffing Bound, and the Huffing Bound is really what gives us the tail inequality. So the Huffing Bound. So now let's look at x, and let's say x is the summation of xi, I going from 1 to n. The xi's are independent, and xi is between 0 and 1. Okay, it's between 0 and 1. If xi was either 0 or 1, it would be called a Bernoulli. But all I need is the fact that the xi's are bounded between 0 and 1. I need no more information about the distribution within this. I'm given that the xi's are independent. And now the way that this bound is stated, so let me state the bound, is x minus the expectation. What is the probability that it deviates by more than t? Is at most, so and this is for some positive t, is 2 times e to the minus t squared divided by n. So n is the number of random variables, and this is the Huffing bound. So what it says is the probability of deviating by more than t. So t is just some absolute number. You're just saying what is the probability of deviating by t. So deviating from the expectation by t, and that's at most e to the minus t squared divided by n. So there's a 2 here, but this, ignore this constant, e to the minus t squared divided by n. So this is written differently from the Gaussian tail that I wrote. But I will now show you that this can be derived. I mean, I'm not going to show the proof of this, but just show you that the rule of thumb essentially gives you the same bound. But before, so actually, yeah, let me stick with, this is the Huffing bound. So let me now look at the rule of thumb just to understand, what's going on. So suppose x is the sum of these independent random variables. What is the variance of x? Well, because these are independent, the variance is the sum of variances. Right? It's the sum of variances. And naively, I can just bound the variance by the expectation of xi squared. Now xi is in 0 and 1, so I can bound this by the expectation of xi, and xi, well, it's between 0 and 1, so clearly the expectation is at most 1. Actually, I could have done this directly over here as well. I can say this is just at most n. So the variance is at most n. So the standard deviation is at most root n. Now write t as follows. I can write like that. So a deviation of t is a deviation of t divided by root n standard deviations. Right? T is rewritten this way, which gives you this, because root n is greater than the standard deviation. Now, by the rule of thumb, the probability of deviating more than t divided by root n standard deviations is e to the minus k squared, right? This is my k. Let me show you this bound again. Remember, just sort of putting it, I'm trying to contrast it with the rule of thumb. I want to write t as k times the standard deviation. I get e to the minus k squared, ignoring constants here, right? So the probability of this deviating by more than t, so this is my t, and I say the k that I get is t divided by root n. So the k that I get is t divided by root n, and so what I get here is if I square this, I get e to the minus t squared over n, which is basically what the Hoeffing bound tells me. So the Hoeffing bound tells me that when I have the sum of independent random variables where each xi, each random variable is between 0 and 1, they're independent, they are not identical. All I know is they're independent. If I have x being a sum of independent random variables between 0 and 1, I can treat x like a Gaussian with a standard deviation of square root n. That's what the Hoeffing bound tells me. I can basically treat this as a Gaussian with a standard deviation of root n. And when I plug in the bounds of the Gaussian, I essentially get this. So up to the constant. There's some differences of constants, but ignoring the constants, this is what I get. So the Hoeffing bound tells me that when x is the sum of independent random variables, I have a sub-Gaussian tail. Now, we are still a far cry from analyzing quicksort. But with these tools, you'll see that we will get closer and closer. So at this point, I'm going to pause. I'm going to pause right now, and I'm going to take any questions, and then we can, I will continue. Go back to the recording. Okay, so now that we have this inequality, the Hoeffing bound, I'm going to tell you, I'm going to sort of switch gears. I'm going to talk about a very different problem now. Something that seemingly has nothing to do with quicksort. Okay, or even randomized algorithms. Let's actually just do some sort of pure statistics. Okay, and let's talk about the problem of just population estimation. Okay, so let's just do population estimation. Estimate the number of whatever have you, Democrats, Republicans, or homeowners, vegetarians, whatever have you, estimate the number of these in a population. Okay? And so you have some, I'll say n people. So you know what n is. Instead of using blue or red, which are sort of, political colors, let me use green. I guess even green technically is a political color. So let me use green, blue, red, some other color. Let me just say it's B. So B is the size of a subpopulation, and we wish to estimate B. By randomly sampling. So what are we going to do? We are going to sample a bunch of people. Now n is too large. So n is this large population. There's some subset. This is B. This is n. We are going to randomly sample some people, and then we're going to ask each person, are you in B? Are you in B? Are you in this population? Are you in the subpopulation? And use that as an estimate. Let's just assume that everyone tells the truth. So this is your standard sampling, statistical sampling. We wish to estimate B by random sampling, and let's say the size of the sample is S, and just to keep things formal and convenient, S is chosen, the sample, I'll say sample is chosen by picking S uniform at random people with replacement. And it's convenient to do it with replacement, so we'll actually assume that a person might be asked again. So we randomly pick up a phone number, we contact that person, and then we do it again independently by picking S uniform at random independent. Okay? So is the setting clear? You basically just want to estimate the size of some subpopulation, and we will refer to the subpopulation size as B. So B is what we want to estimate. N is the total number of people. S is the number of samples. This is our budget. This is how many people we can sample. The question is, how do S, B, and N relate to each other? How are you going to use this to sample? So, what I'm going to do is I'm going to say, so we sample these S people, right? So S is the sample. And suppose B sub S, people in the sample, are in the population, are in the subpopulation. Right? So you sampled S people. B sub S people in the sample are in your subpopulation. What is your estimate of B? What should your estimate of B be?
Just the same fraction as, like, we just say, like, we're just gonna multiply that number of people, like, divide it first by the sample size and then multiply by the population size.
By the population size, right? So our estimate is going to be B sub S divided by S times N. Right? You're saying this is my empirical fraction. This is the empirical fraction of people who have the subpopulation. I multiply this by N. This is my estimate. What can you say about S? How large does S have to be to get some kind of accuracy? And now let me state a theorem here. And we'll see that it follows directly from the Huffing inequality. I'll say that for any alpha greater than 0 and delta greater than 0, one can estimate B up to additive error alpha n with probability at least 1 minus delta using S, the sample size of log 2 divided by delta divided by alpha squared. Okay, formally what I'm going to say is that the probability that B sub S divided by S times N right? This is your estimate. The true answer is B. The probability that this deviates by more than alpha times the population size is at most delta. This is often called the accuracy, and this is called your confidence. Is there something interesting you observe about S? Is there any dependence on N? Is there any dependence on N? No. There is no dependence on the population size. No dependence on N. Of course, for someone who knows statistics, maybe this is obvious, but you'll often see people say, oh, how can such a small sample say something about, I don't know, the fraction of vegetarians in the United States? And you say it doesn't, the size of your sample does not depend on N, regardless of what N is. If you're looking for an additive percentage error, then it only depends on the accuracy and the confidence that you want. It has no dependence on the size of the population. Okay? So raise your hand if you've already seen this statement before, or if you're aware of this. Okay? Alright, so why don't we actually just do a formal proof of this? It's a direct consequence of the Huffing inequality. So let's prove it, and it's just, we're just going to plug in the Huffing bound pretty much as is. So let xi be the indicator random variable for the ith sample to be in the subpopulation. Right? This is an indicator. This is going to be 1 if the ith sample was in the subpopulation and 0 otherwise. Okay? Just to sort of put this back to you, B sub s. B sub s is simply the summation of xi, I going from 1 to s. Okay? So now, basically what we're going to do is just apply the Huffing inequality on this, the Huffing bound, I'm sorry, not the inequality, Huffing bound. So what is the expected value? So I'm just, for convenience, I'm just going to define this as x. The expected value of x by linearity of expectation, so this is expectation summation of I going from 1 to s of xi, is the summation I going from 1 to s of the expected value of xi. Now what is the expected value of xi? This is exactly the probability that the ith person was in your subpopulation. But you're sampling uniformly at random, so this is exactly equal to b divided by, by n. Right? This is the subpopulation size, and this is the total. So what you get is, by linearity of expectation, you get SB divided by n. Right? This is the expected value of B sub s. Okay, now let's apply the Huffing bound. The probability that x minus the expectation that this deviates by more than, so now I can plug in something over here. I'll say more than alpha times s. This is at most 2 times minus alpha square s square divided by I'm sorry, it's not n, but the number of samples, which is s. So let me bring out the Huffing bound again so that you can see exactly how I did this. So I'm sorry, there's a bit of overloading of notation here. The n over here is the number of random variables, which is little s. Right? That's little s. And so what you said is that the probability of deviating by alpha s, that is t, is 2 times e to the minus t squared, that's alpha square s square, divided by the number of random variables involved, which is s. Right? So you get exactly this. Okay, so that's going to cancel out. Now I set my s to be 2, it should be natural log of 2 divided by delta divided by alpha square. So if I plug that in, so this, I get this is equal to 2 times e to the minus alpha square, and this was log 2 divided by delta divided by alpha square, and I basically cooked all of this up so that this thing is exactly delta. I'm sorry, this thing is exactly delta. So the probability that b sub s, which is the expected, which is the number of people you saw in your subsample, the probability that that deviates from the expected value by more than alpha times s is at most delta. Okay? Of course, what you wanted to know was the estimate. Remember, your estimate was actually b sub s divided by s times n. But you'll see all you have to do is just multiply this expression by that. So what we're going to say is, therefore, the probability that x minus the expectation of x, the probability of this was more than, this was less than alpha times s, this is at least 1 minus delta. All I did was just flip things around. Now in this expression, let me just multiply the entire expression by n divided by s. Right? So this is just saying that, remember, x was b sub s minus the expected value of b sub s is less than alpha times s. The expected value of b sub s, that's over here. So I just write this as b sub s minus sb divided by n less than alpha times s. And let me now multiply this entire expression, like multiply both sides by n divided by s. And what I get is b sub s times n divided by s minus b is less than alpha times n. And this is exactly the estimate minus the truth. So I'm just saying that this is the same thing as this. These are identical. So the probability that your estimate minus the truth is less than alpha times n is at least 1 minus delta. And therein, this is basically the proof. This argument, just an application of the Hoeffing, is an immensely important part of the analysis of randomized algorithm. This argument appears over and over and over again. And so it's good that you get familiar with it, because later on in the course, I'm not going to work it out in full detail. I'm just going to say, by the Huffing bound or by the Chernoff bound, blah holes. Okay? So any questions about that? Maybe I'll just restate this. What happened was I took the indicator random variable for the ith sampled to be in the subpopulation. I know that my estimate, my estimate is going to be b sub s times n divided by s, where b sub s is just the number of people in the subpopulation, which I wrote as a sum of indicators, independent. All the xi's are independent. So the xi's are independent. And because they're independent, I can then use the Huffing bound. So I use the Huffing bound on this. So what is important is you convert whatever your algorithm is doing. Your algorithm here was just sampling a bunch of people, looking at the fraction, and then multiplying that by n. You try to write that as the sum of independent random variables. And once you write that as the sum of independent random variables, then you can apply the Huffing bound. And once you apply the Huffing bound, you sort of go through the motions over here, and you can basically derive the right choice of S. And remember, S over here was essentially log 2 divided by delta. I'm sorry, the natural log. My apologies, should be a natural log. S is the natural log of 2 divided by delta divided by alpha squared. Any questions? Any questions?
If you wind up asking the same person twice, isn't that person's answer the second time dependent on their answer the first time?
That's right. But on the other hand, the random variable xi, so it's like saying that.
But you chose the people independently, so it doesn't matter.
Exactly. I choose each trial is independent.
Yeah.
So the trials are independent of each other, which means that the answer to one trial does not depend on the answer to another trial if you don't know, like before making the choice. Does that make sense?
Yeah, that makes sense.
Yeah. Meaning, conditioned on the value of x1, x2 still behaves like what it used to behave.
Yeah.
Okay. So let me proceed here. I want to go back to understanding this bound that we just found, because this bound is, what was the bound? It was this. So let me sort of write this out in a separate page. I'll say the samples was log 2 divided by delta divided by alpha squared. And the bound, the guarantee that I got is the probability of the estimate minus the truth. The probability that this was more than alpha times n is at most delta. Right? Now let's look at this in terms of trying to understand two things. Ideally, you want to decrease both alpha and n. When you decrease alpha, your accuracy increases. When you decrease delta, your confidence increases. So to increase your accuracy, you have to decrease alpha. That's expensive. And why do I say that? Well, if alpha goes to alpha divided by 2, then S becomes 4 times S, right? So if you have alpha, because of the quadratic dependence, you have to increase by 4 times. So if you wanted a tenfold increase, so you wanted to increase by 1 decimal point, you now have to sample 100 times more. But on the other hand, to increase confidence, you will decrease delta, and that's cheap, because when delta goes to delta divided by 2, because you have a logarithmic dependence here, the increase is only additive. The increase is only additive. It's basically s plus log of 2 by alpha square, and this is much smaller than s, meaning that to increase your confidence, you only need an additive increase in your sample size. To increase your accuracy, you need a multiplicative increase in your sample size. This is very important because what happens is it's easy to increase your confidence. It's cheap. And this, the fact that there is a logarithmic dependence here, plays a role in many results. On the other hand, the quadratic dependence that you see here is also something that will appear over and over again in many different kinds of results. The first thing to understand is when you look at this, is it tight? Do you really need this quadratic dependence? So the first question is it tight? Meaning the quadratic dependence of the error parameter, I should say quadratic, on the error parameter alpha. Any thoughts? Like, do you really need this? Does the question make sense? Yeah? So do you really need this dependence? The answer is, it's subtle, but the answer basically is yes. In the worst case, you do. Yes. I'll qualify this by saying in certain regimes. Can anyone hazard, so I'll actually show how you can prove that. Can anyone hazard a guess? How would you actually argue that you need these many samples to get an additive estimate of alpha n?
I guess intuitively, like, it's very easy to tell, like, because x is like because the sum of your random samples is going to be kind of quadratic, and so like, or not quadratic, Gaussian. So it's like most of the probability mass is in the middle.
Yes.
It's kind of difficult to distinguish when you're like between like the true mean and things that are close to the true mean.
It's true.
Like it's easier to distinguish at the tail.
Yes, that's true. The question is, why is there a quadratic dependence? You're almost there. And the quadratic dependence, like, why is it not this? Does that make sense? Like, why isn't it linear? Why is it actually quadratic? Could it be anything better than quadratic? Could be like, maybe alpha to the 4/3 or 3/2 or something less than 2? So let's investigate this question further. If you look at what we have done, we are basically estimating parameters of a binomial distribution. Right? Because essentially we're estimating the bias of a coin. So what I mean is, if you look at any individual trial, so let's go back to this xi here, which is the indicator for the ith member. Xi is a Bernoulli with, where the probability that xi is 1 is exactly b divided by n. And you're trying to estimate b, which means effectively you're trying to estimate b divided by n. So now I can restate the entire question, whatever happened here, to saying I have a coin. and I want to estimate what is the heads probability of the coin, right? How many coin flips do I need to get an accurate estimate? Right? How many coin flips do I need to get an accurate estimate for the heads probability of a coin? So let me, again, sort of abstracting this discussion out, let me just say X is a Bernoulli where I'm just going to call this as P. Doesn't matter, right? So this is P. So P is the parameter. And what I'm looking at is really the binomial distribution BSP, where S was the number of samples. So I'm looking at BSP. And this is a binomial distribution. Binomial, and this is basically the number of heads, or you can think of the number is the size of subpopulation in the sample, which we had also referred to as B sub S, right? B sub S is distributed as a binomial. Okay? Suppose P was equal to a half. So it's actually an unbiased coin. Or another way to think of it is half the people lay in your subpopulation. You would like to estimate this up to some error. Okay? So this is saying we want to estimate P up to an error, and let me use up to an error of alpha. Okay. So, right, so this is the setting, right? And I'm going to prove to you, using this setting, I'm going to prove to you that this quadratic dependence is necessary. You cannot beat this quadratic dependence. There are situations where you cannot be, well, actually the answer is more complicated. I should cut to the chase. There are situations where you cannot beat the quadratic dependence. On the other hand, there are situations where you actually can improve on the quadratic dependence for certain regimes of the parameters. And it's important for us to understand both these regimes. So here is the regime where we cannot beat the quadratic dependence. Suppose the probability was half. So you want to estimate this probability up to an error of alpha. Let me write this out as saying, what is the probability? Okay, so we had S trials, right? S flips. What is the probability of seeing H equal to, I'll say, S divided by 2 plus alpha S heads? I don't think we even need the H. What is the probability of seeing this? Okay, can someone tell me what the expression is? What is the probability of seeing exactly these many heads? Yes? It's an unbiased coin. There are S flips. Each flip is equally likely to be heads or tails. What is the probability of seeing exactly S over 2 plus alpha S heads? Yes, someone? Have I lost everyone here?
It's like the number of flips that you're doing, which I guess is
S.
Choose
Okay.
the number times 2 to the times 1/2 to that number. It's not super well explained.
That's the probability, right? You have S flips. First, you choose which are the ones that are going to be heads. So you have to choose these many of them. And you say this is going to be a heads, that's a heads, that's a heads, that's a heads, and everything else is a tails. So the probability of seeing this specific instance is 1 divided by 2 to the s, because all the probabilities are a half. Right? So this is the probability of seeing alpha s heads. Does this make sense? So please ask me questions at this point so that I can clarify this. This is the probability of seeing exactly s over 2 plus alpha s heads. Yes?
Yeah.
Okay. Just looking at the chat window. Okay. Now, this is the probability of seeing exactly alpha s heads. So let me just write that out over here. So 1 divided by 2 to the s, s choose s over 2 plus alpha s. Now, I'm not going to work this out in gory detail here. So whoever's the scribe, you're going to have to sort of complete the proof of, you'll have to figure out the details. But basically, you use Stirling's approximation. Use Stirling's approximation. So the largest binomial coefficient is when alpha is equal to 0. So when alpha is equal to 0, you'll see that what you get over here is essentially roughly, I mean, ignoring the lower order terms, will be 2 divided by root pi s. Okay? Ignoring the constant, what you see is it's theta of 1 divided by square root s. Okay, now why is the alpha equals 0 case important? Because if you saw exactly s over 2 heads, then your estimate will be perfect. You will nail it down exactly. So with probability essentially 1 divided by square root of s, you will nail it down exactly. But what this says is there is a significant probability that you will not nail it down exactly. Indeed, you can show that, again, using Stirling's approximation, you can show that this is okay. So I'm gonna write down an expression. This is approximate, and I don't want to sort of worry about the constants. Again, the scribe using Stirling's approximation, you figure this stuff out. So this is in some sense what it is when alpha is equal to 0. You get something that looks like this. So if you did the general, you did Stirling, you'll get that. So if you look at the binomial coefficient, the middle binomial coefficient when alpha is equal to 0, this is when you get perfect estimates. This is essentially 1 divided by root s. That's the probability. But if you look at it for general alpha, if you apply Stirling's approximation, this is the expression that you get. So why is this interesting? This says that when alpha is less than 1 over root s, then e to the minus alpha square s, this is essentially just a constant. What this means is that for all choices of alpha being less than 1 over root s, you are essentially equally likely to see that many heads as well. Another way to say this, and again, I'm just giving you the intuition, the math explicitly, I'm not worrying about the constants here, is that you are essentially equally likely. So what I'll say is essentially the probability of getting s over 2 plus root s heads is essentially theta of the probability of getting s over 2 heads. Or another way of saying this is the probability of seeing s over 2 plus capital delta heads is theta of the probability of seeing s over 2 heads for all delta, which is in the range minus root s to root s. What this means is that you're equally likely to see s over 2 plus delta heads where delta is in this range. And if you see s over 2 plus root s heads, then your estimate for the bias is half plus 1 over root s. Right? If you see more heads, then you'll estimate the probability is higher. So your estimate for the probability is half plus 1 over root s. Aha. So this is your alpha. This was the error that you were getting. And so 1 over root s being alpha means that s is 1 over alpha squared. Sorry. So what this says is when you choose s samples, you are likely to incur an error of 1 divided by root s. Flipping it around, it says that if you want your error to be alpha, you need 1 over alpha squared samples. And this is the analysis just for the special case of the unbiased coin. And what the Huffing Bound tells you is this essentially carries over for sort of any population estimation situation. So even if the bias is not half, but the bias is away from half, its bias is essentially something between 0 and 1, regardless of what it is, this is the bound that holds. Does this make sense? So you see that this dependence, this quadratic dependence, is necessary, that there is a situation where the quadratic dependence is necessary, and the situation is actually the simplest unbiased situation. Any questions at this point?
Am I audible?
Yeah.
Oh, thank God. Yeah. So I was just wondering, if we do intend on losing the quadratic dependence, decrease it by some factor, what is the result on, say, like, do we get a different ones if we fiddle around with maybe the accuracy?
So, sorry, going back to this, you mean, I don't know, maybe I don't understand. Can you say that again?
So, I'm saying that, so my question is that how would, like, if our goal was to, say, maybe backtrack somehow and use, and suppose it's not possible for us to get a quadratic, like it's too expensive maybe.
Good, yes.
So in that case, what is there any...
Good, so good. So the question is, you're saying, but suppose I don't have that many samples, what can I infer?
Yeah.
That's another way of putting it. And this is exactly going to be like the next part of what I was hoping to talk about today, but we're almost done with time. But let me lead off on that, which is exactly the question of, can you do anything better? Like, this is just, this analysis says that you cannot do anything better when the bias is a half. But you can ask, if you spent less than 1 over alpha squared samples, do you get any information at all? And the answer is yes, you actually do get information. Another way of thinking about this is, it is expensive to accurately estimate the half. But it's not that expensive to just get a ballpark estimate that my bias is between 1/3 and 2/3. That I can do pretty quickly. So what I will actually show you, my next part is to say, we were looking at BSP. So you fixed your P, and if you let S go to infinity, it's like a normal distribution. And in the normal distribution, you work out the standard deviation, and essentially this tells you that this 1 over alpha square is essentially necessary. But, sort of going off from the previous question as to really what can you infer under if you cannot afford these many samples. Really, given any number of samples, what is it that can be inferred? Let me now state another theorem, and I will contrast it with the previous one. The proof of that uses another variant of the Huffing Bound called the Multiplicative Chernoff Bound, which gives you something sharper for this situation. So let me now state this other theorem. So again, I want to state it in terms, instead of population, let me now state it in terms of estimating the bias of a coin, because we've said that these are basically the same thing. So now I'll say for any, I'm sort of stating this in a somewhat convoluted way, but you'll see why. For any alpha and delta greater than 0. So again, let me now pull up my previous theorem here. Sorry, I just seem to have dropped it. Okay. So remember, I parameterized it by alpha being the accuracy and delta being the confidence. And I said I want to estimate B up to an additive error alpha. So let me, again, I'm sort of in this binomial situation, right? My aim is to estimate P. I'm basically doing parameter estimation for the binomial, which is really this subpopulation estimation problem. And okay, now sort of let's look at this a little carefully. I'll say if P was greater than alpha, then one can estimate P up to a constant multiplicative factor with probability at least 1 minus delta using a sample size which is, again, I ignoring the constants, basically O of log 1 over delta divided by alpha. No quadratic dependence here. Now this is a linear dependence. So if the probability, so I'm saying here's a threshold alpha, here's delta. And another way of writing this, I'll say the probability that the estimate is within P over 2 to 2 times P. This is your multiplicative estimate. The probability that it's within this is going to be at least 1 minus delta. So there is no square. This is linear. So this says that in the as long as your probability is at least alpha, then you get some kind of estimate. You get a multiplicative estimate. So note that when P is actually alpha, my estimate is also an additive alpha estimate. I'll write this down. When P is actually theta of alpha, then the estimate is also an additive alpha estimate. So I have actually estimated the bias up to an additive error of alpha when P is theta of alpha. So what this is saying is that indeed I'm actually able to beat the 1 over alpha squared dependence if the bias itself is proportional to alpha. So this is the interesting point here. As the bias, as it becomes unbiased, when the probability is a half, that's actually when it's the hardest. And if, so just as an extreme case, think of it when p is 0, then your estimation is always perfect. And when p is a half, that's when it tends to be the hardest to estimate. This theorem can also be proven by a variant, by something called the multiplicative Chernoff bound. I don't want to get into that right now because this is the end of the lecture. Instead, I'm just going to put this, I'm going to show you the previous bound so that you can sort of contrast them, and then I will take questions. Okay, remember, so here I have alpha and delta. I want additive error. So again, you can ignore the n and just say you have additive error alpha on the bias of a coin. And the cost was essentially log 1 over delta divided by alpha squared. And here, I'm saying you estimate with multiplicative error. Not additive alpha error, but multiplicative error. So you get an estimate that's between p over 2 and 2 times p with probability at least 1 minus delta. So you get an accurate estimate, except your number of samples is just essentially log 1 over delta divided by alpha. So there's this linear, or I guess it's just inverse, is an inverse linear dependence as opposed to an inverse quadratic dependence. And observe that when p is actually theta of alpha, the estimate is also an additive alpha estimate, right? So you're actually able to do better than the case for this for the unbiased distribution that we saw. So I'm going to end here, and in the next lecture we will do a proof of this using the multiplicative Chernoff bound. And once we have the multiplicative Chernoff bound, we'll actually come back and start talking about the analysis of randomized quicksort, and sort of after the sort of detour in statistics, we'll go back to algorithms.